So students, capacitance of a capacitor is given by the formula C is equals to Q by V. But if I ask you that what the capacitance depends on, so capacitance depends on according to this formula. That is, capacitance is equals to epsilon naught A by D. So capacitance is directly proportional to the area. So this is for parallel plate capacitor. So capacitance is directly proportional to the area of the plates and inversely proportional to the distance between them. Lesser the distance, more will be the capacitance. Now some of the time, now another thing is that what is the unit of capacitance? So SI unit of capacitance is,
Actually,
yes,
since Saurav is joining,
so uh, for parallel plate capacitor, C is equals to epsilon naught A by D. So what are the SI units of capacitor? That is farad. Okay, so capital F, and 1 farad is equal to 1 coulomb per volt. So it is coulomb per volt. So 1 coulomb per volt is 1 farad. And what symbol you will have for capacitor? So this symbol you will have for capacitor, two parallel plates and this. So this is the symbol. And for if the capacitance is variable, then this is for the variable capacitor. Okay. So mostly we have the farad is a very big unit. So the units that we use is 1 microfarad, that is equals to 10 raised to the power 6 farad, and we have 1 nanofarad, so nano means 10 raised to the power minus 9, and 1 picofarad, so picofarad is 10 raised to the power minus 12. So you must know these prefix micro, nano and pico. Now if we do this, if we derive this formula, this is quite simple and it is very important for examination point of view. So definitely we are going to have a question from the capacitor. It's sure that in board you will have a question from the capacitor. So this is suppose plate 1 and this is plate 2, and these plates are separated by distance. So this small distance, this diagram is not as per the scale, so they are separated by a very small distance. And first of all, we are not taking any medium, so it's vacuum in between the plates, and A is the area of each plate. So this plate has area A and this plate also has area A. And these two plates have charge, so this plate has charge plus Q and this plate has charge minus Q. So we can show it over here. Now the surface density of plate 1 is given by nu. Nu is the surface density, and that you know that surface density is charge per unit area. So that's the surface density. Now what will be the surface charge density of plate 2? So it is minus nu. Of course, minus Q by A. So students, we have to, what we need to do, we need to derive this formula. This is what we are going to derive, that C is equals to epsilon naught A by D. So now in exams, whenever there will be any derivation, you already know that relation, you already know that equation. So write that equation in front of you that you are going to derive. You need to bring these variables C, A, D. And this is the only formula of C that you know. So C you can bring from here. And from where you are going to bring A and D. So that we need to see. Now, what is the, so here we will have three regions. One is region above the plate A. So we take it as region 1. So region 1, or you can say outer region 1, what will be the electric field? So electric field, we already know, we did the application in as an application of Gauss law, that electric field due to parallel plate capacitor at any point, so whether it is P, Q, R, whether it is near to it or little bit even far away from it, so that is for infinite plate. So the electric field at any of these points is given by nu by 2 epsilon naught. And of course, if it is positive, then the direction of electric field will be outward. What I want to say is that this electric field is independent of the distance. How much is the P away from the plate? How much is Q away from the plate? How much is R away from the plate? Even for this point S also. So the electric field is independent of the distance. So it is constant because epsilon naught is constant and charge density of the plate is also constant. So this is constant. So it means, so what is the direction of electric field due to plate 1? So it is positively charged plate, so that will be the direction of electric field due to positive plate. And what will be the direction of electric field due to negative plate? So it will be towards the negative charge. So this will be the direction. So the directions are opposite, and this E positive is independent of the distance, and this E negative is also independent of the distance. So both will cancel out each other because magnitude is same and they are in opposite direction. So electric field is a vector quantity. So the net electric field in region 1. So this is due to plus Q, this E positive, and due to positive plate, and this minus 2 by epsilon is due to, this electric field is due to the negative plate, and they will cancel out each other, and the net electric field in the region 1 is 0. Now let us take this as region 2. So here at this point, electric field due to positive plate will be outward from the positive plate, and for negative it will be inward. So here again the electric fields are in opposite direction, so they will again cancel out each other, and in region 2 this electric field is equals to nu upon 2 epsilon naught. This is due to E positive and E negative, E upon 2 epsilon naught. Or you can also take it as if this direction you are considering as positive, and so this direction will be negative. So here this was E positive in the positive direction, and this was E negative. So the magnitude is same, but this negative sign and this plus sign, they are telling you the direction. So here this plus direction means, so the upward direction is positive. So here this E negative can be taken as positive, and this E positive direction is downward, so this can be taken as a negative. But the net is they are equal and opposite, so net will be 0. Now we have one more region which is between the plates. So let me take this point, any point in between the plates. So what is the electric field here? It will be towards the positive plate for positive, and for negative plate it will be, sorry, for positive it will be away from the positive charge. The field is always away from the positive charge, and for negative it will be towards the negative. So here you can see both the electric field are in same direction. So between the plates, region between the plates, the electric field is going to add up, and the electric field is due to, so both are in same direction, so they are going to be added up. So this is equals to 2 nu upon 2 epsilon naught. That is equals to nu upon epsilon naught. Now, as you can see that this is the formula I am going to derive. So there is no surface charge density in this formula. So I need to put the value of nu here. This I want, okay. I don't want E, I don't want nu. So this sigma, sorry. So sigma I have to remove. So sigma is equals to Q by A. So put the value of Q by A into epsilon. Now see, I want epsilon naught, I want A. So I have two of the variables that I need, but I still don't want Q. So this I can write as equation 1. So what will be the direction of electric field? You can clearly see the direction of electric field is from the positive plate to the negative plates. So direction of E, because E is a vector quantity, so you need to tell. So direction of E, electric field, this electric field is, so this was the magnitude, I am telling the direction now, is from positive to negative plate. Okay. And electric field is uniform, in between the plates. So now this uniform electric field, for the uniform electric field, potential difference, what is the potential difference? Potential difference is equal to ED, we did it yesterday. So V is equals to, so this is the potential difference between the plates is equals to E into D. So these are the two charges, plus Q and minus Q. And now this, what is E? E equals to one by, so what is, this is your E, right? Equation first. So put this value of E over here. So that's equals to, so you can write it in next line also. So here you can write, we know that V is equals to ED, and or V is equals to, put the value of E, that is Q upon epsilon naught A. So intentionally I need to bring D, so from this formula I have got D, and I need to eliminate E. So E is eliminated by putting the value of E over here, so into D. So using first, and now you need C is equals to epsilon naught A by D. So you have A by D. So you don't need V and Q. So this is V upon Q is equals to D upon epsilon naught A. So you need it in the form epsilon naught A by D. So reverse it. Q by V is equals to epsilon naught A by D. And what is now Q by A? Q by A is capacitance. So obviously is capacitance. So epsilon naught A by D. So this is the formula that we were supposed to derive capacitance between the plates. So it's so simple, students. You need to have only this formula and this. So this is the capacitance of the capacitor, parallel plate capacitor. Now, the next thing is that we derived it for vacuum because epsilon naught is telling you that this is for vacuum. Now, if you insert dielectric between the plates, so what will happen? What is the effect of dielectric? So this is the dielectric that, so these were your plates, positive charge plate and negative charge plate, and you have inserted dielectric in between the plates. So what will be the impact of this dielectric on the capacitance of the capacitor? What do you want? You want capacitance to be more? Yes, you want to more. You want to store more electric energy in the capacitor. That is the purpose of capacitor, to store electrostatic potential energy. So we want this capacitance to be more. So for that we are inserting dielectric. And now what will be the formula if you are inserting dielectric? Then we can also write this as C naught. This formula we can also write as C naught. C naught telling you that this is for vacuum. Okay. And now the permittivity of this dielectric can be written as epsilon naught K. We did it in Coulomb's law also. So in Coulomb's law, these were the two charges. Let me just remind you because that's also important. And the distance between the charges was R. So the Coulomb's force between these two charges was given by K. So let it be, let both of them can be, positives, a capital Q and small q, Q1 and Q2 also you can take. So K, Q1, Q2 upon R square. So that's the magnitude. And like charges, so that will be the direction of the force. So here, what is the value of K? K is equals to 1 upon 4 pi epsilon naught Q1, Q2 by R square. Now suppose if I put in between the charges, if I put a dielectric, this dielectric I put, so what will be the formula? So this formula is for vacuum. And if I have dielectric in between the charges, then the formula will be for any material. So then the formula will be, instead of epsilon naught, I will have 1 upon 4 pi epsilon Q1, Q2 by R square. And what will be the value of this epsilon? Epsilon is equal to epsilon naught K. So 1 upon 4 epsilon naught. So this K is different from this K. This is, you can see this is small k, we write it as small k. This is Coulomb's constant. and this K is dielectric constant, and Q1 Q2 by R square. So this was the force in vacuum, this is the force in medium with dielectric constant K. So students, at two places we use this permittivity. So this is permittivity of the medium, and this is the permittivity of free space, or you can say vacuum. So, and K, you can see, is written as epsilon upon epsilon naught. And the value of this K is, so if it is for C, for some medium, like here when the force was for medium, so I replaced this epsilon naught with epsilon, right? And put the value of epsilon. Same is the case here. Replace this epsilon naught. So instead of C naught, I have written C. Okay. And for epsilon naught, I will write the permittivity of the medium and into A upon D. So same thing as I have done here, I'm doing it here. So this will be the capacitance when the material whose permittivity is epsilon I have inserted. So this is the permittivity of this dielectric. Now put the value of permittivity is equals to epsilon naught K. So C is equals to epsilon naught K A upon D. Now this was my capacitance before I inserted this dielectric. So I can write it as C is equals to K C naught. It means my capacitance has increased. So here I have inserted, after inserting dielectric, so after inserting dielectric with permittivity epsilon, so this formula will be this, and I have just put the value of epsilon, that is equals to epsilon naught K, and then I have, so this is equation number 1. So I have used equation 1 over here. So using equation 1. So students, I am very much concerned about the value of this K, because now the new capacitance is K epsilon naught. So this value of K is always greater than 1. So this is greater than 1, so that is why the C capacitance will be greater than C naught. So another formula of K is C upon C naught, and this is greater than 1. So that is why this C in the dielectric is greater than C capacitance of in the vacuum. So, and you can derive this K, we have written as epsilon upon epsilon, C upon C naught. But now, as you know, that this in the formula, you know that that C is equals to Q by V. So C is inversely proportional to V. So if you write this K in terms of V, because C is equals to Q by V, so this V naught will come upside and V naught will come upside and V will come downside. So K is equals to V naught upon V. So putting this value of C here. And further, as E is equals to VD. Students, I hope you have understood this. So this C is equals to Q by V, and this is equals to Q by V naught. So this Q will cancel out, and this will be V naught by V. And then V is equals to, so V is equals to ED. So here also this is E naught D upon ED. So D will cancel out. So that is what we need for this K. And this K is, what is this K? K is dielectric constant. This K was your Coulomb's constant, 1 upon 4 pi epsilon. So students, this is what we will need in some numericals also. Now, proceeding further, let us do one example based on the concepts we have just done. Let us do example 2.8. So 2.8, we have a slab of material with dielectric constant K has the same area as the plates of parallel plate capacitor, but has the thickness of 3/4D. So these are our plates, but these are our plates. So area is same, but this is the distance D between the plates of the capacitor, but the thickness of the dielectric is only not this, it has not filled this full length, it has just filled out of 3/4D. So this is dielectric in 3/4D, and this is vacuum. So this is vacuum in 1/4D. I have vacuum. Okay. So how is the capacitance changed when the slab is inserted between the plates? So what's the new capacitance when this slab was inserted? So when there was a vacuum, at that point of time, electric field between the plates was, so E is equals to V naught by D. So this was the electric field between the plates when there was no dielectric. So this naught is telling you that vacuum is there. So always keep this thing in your mind. And now the dielectric inserted. So as the dielectric inserted, then this will be equals to, I've already written this formula. So E is equals to E naught by K. Yes, E is equals to, so taking E that side and K in the denominator, bringing it. So E is equals to E naught by K. Then what will the potential difference? So potential difference, you know, is equals to E into D. So here you have used the formula E is equals to, sorry, V is equals to ED. Here you have used the formula K is equals to E naught by E. And again we are using this formula V is equals to E naught D. Now look at this symbol V. So V is, so this E was after, this E was after inserting. So students, these symbols are for vacuum, E naught, and this symbol, when naught is not there, it means this is after inserting the dielectric. Okay, after inserting the dielectric, for this E also, for this V also. Okay, and the C will be the symbol, right? So let us write V first. So V is equal to ED, right? That's the formula. So V naught is equals to E naught D So the electric field, when there was vacuum, V naught by D. When there is inserting, after inserting the dielectric, then it's E naught by K. So V is equals to ED, right? Now, this potential difference between the plates will be due to, we have two things now here. Vacuum is also there, and we have dielectric also there. So we have two things. So potential due to this potential difference due to vacuum will be, so ED, so here for the vacuum it will be E naught into, what is the distance? Distance is 1 by 4D, right? Plus, now the contribution due to this dielectric in the potential difference between the plates of the capacitor. So this will be written as, so what is the electric field here? This will be E, yes, so E into, what is the, how much is the D? D is 3 by 4 D. So now this V is equals to E naught 1 by 4 E naught D plus, what is the value of E? So this is your value of E. So put this value of E here, you will get E naught by K into 3 by 4 D. Okay. Now, this can be written as, you can take E naught D common. So E naught D is common. And what do we have? 1 by 4 plus 3 by 4 K, right? This is what do we have. And student, what is E naught D? So E naught D is V naught, right? So we can write here V naught. So V naught equals to, now it's 4, K will be the LCM, and this will be equals to 4 K, so multiplying K in the numerator and denominator, so 4K will be there, so K plus 3 upon 4K. So that is the potential difference. So this was the potential difference between the plates when there was vacuum, and this V is the potential difference. So tell me, is this V increase or decrease? So for that we need to know this value of V naught. So which one is greater? So K, obviously it's 4K. So this value will be lesser than 1. Okay, because you are multiplying K here with 4. So multiplying K with 4. See, what does this mean? K plus 3, and you are multiplying this 4 with 4K means K plus K plus K plus K. This is the meaning of 4K. And here K plus 3 means K plus 1 plus 1 plus 1. Now this K is same, but these 3K, their value of K is greater than 1. So obviously this 3K will be greater than 3. So it means this whole will be lesser than 1. Okay, so this is lesser than 1. So multiplying V naught with lesser than 1, it means V is lesser. So it means that V, potential difference, it means potential difference after inserting dielectric potential difference V decreases by factor K plus 3 upon 4K. So by this factor it is decreased. Fine. While the charge on the plates remain the same, while Q naught on the plates remain unchanged. So now what will be the capacitance after inserting the dielectric? Capacitance is equals to, so Q naught is not changed, so that is why I am writing Q naught, okay? Otherwise it will be Q by V, okay? So you can write it as Q by V also, Q by V, after inserting the dielectric. So the symbols that I am using after inserting the dielectric is E, V, okay, and C. What about Q? Q is same, so there is no change in Q. So Q is Q naught as before. So these are the symbols that I am using after dielectric. And for vacuum, I am using the symbols when there was vacuum: E naught, V naught, C naught, and Q naught. So here Q and Q naught are the same. These three are different. So C is equals to Q naught by V. Now putting the value of V from here, what do we get? So this is Q naught, and reciprocal of this, because this is 1 by V, so doing the reciprocal, I get V naught and 4K upon K plus 3. So this is the capacitance, and as this factor K plus 3 upon 4K was lesser than 1, we just proved it, so obviously reciprocal of it, 4K plus K by 3, will be greater than 1. And this is C naught. Q naught upon V naught is C naught. C naught 4K upon K plus 3. So it means the capacitance is increased by the factor 4K upon 4K plus 3. Okay. So students, I hope you have understood this concept of capacitance between the
Yes, sir.
plates of the capacitor. So students, that's all for today's class, and see you tomorrow.